because there's only like 7 people here, so whatever. But yeah, so the idea of this talk was to kind of look at some of the code inside of Geth, and use that as a way to understand a little bit about how Geth works, and also a little bit about how Ethereum works, because you can't really separate the two. So you know, useful to understand both. And specifically, what I'm going to look at is the RPC method called Eth Call, and this is Eth_call. And if you're not aware, that RPC method is essentially it allows you to sort of execute not really transactions, but messages against contracts. So just like you give data to a contract and see what happens without actually putting a transaction on chain. And so this is super useful, obviously on front ends when you want to query the state of a contract. In Solidity, if you put a public variable, this creates a getter function, and sort of under the hood, how that works is that you send data to the contract. In the first 4 bytes, they act as a selector, and it says, so the Solidity compiler will put some code into your contract that picks like, oh, okay, you wanted to call getOwner, and then it will execute the code path that loads the owner storage slot and returns it. Right. So I think the reason why this API or the RPC method is so interesting is because it doesn't touch a lot of the messy things inside of Geth. So if you send a transaction, you're probably aware that you'll send this transaction to a Geth node, and then it goes into this mempool, and then there's this whole thing whereby people, they gossip these transactions around, and it's this whole complicated thing, and then eventually it gets pulled in by a miner and executed, and it's very complicated. There's a lot of like layers of indirection between I click the button, I send the transaction, and something actually happens inside of Geth. Eth Call is way cooler because Eth Call, basically, you click the button, and then it immediately goes to this sort of endpoint, this function inside of Geth, and it immediately does all the cool like EVM stuff, right? So it's a very like, if you want to understand a lot about how Geth works and a lot about how the EVM works, you just sort of follow the path of Eth Call, and you'll get a very clear idea of like, it's very tangible because you click the button and things happen, right? And I think as I start going through this code, I'm kind of going to just walk through it, and then as people have questions or if there's things that they want to look at even more, feel free to speak up. There's no reason for this to be a lecture. But yeah, I'm kind of just going to walk through it, and you'll get a good idea of like how Ethereum works under the hood. It's very clear as you read the code what's going on. So essentially, let's start here. Geth has this interesting like API thing that sort of automatically generates the RPC endpoints. So whenever you're seeing these like, call, like this is gonna add like it's gonna create an RPC endpoint for Eth_call. But when oh, bigger, yeah.
I thought you were required to add like a method to web3.ext, something like that.
Yeah, I don't know the exact details of like how this gets converted into the RPC endpoint, but at a high level, there's very little between, if I click a button on a front end and it makes a query to a node, there's very little in between like this and actually getting to this function, which is.
If you go to the tree under internal.
Go to web3.ext.
That one, and then go to that. And
yeah, I see. Okay.
JS. Yeah, that's where I usually add stuff. And then this allows me to like call an RPC.
Got it. Okay. Cool. I haven't looked at this before. This is interesting.
Just give it a name, like a custom name.
Yeah.
And then it calls as long as the method is the same name as the name.
Cool. Yeah. I see. Yeah, but essentially you have you have some like code that transforms this function into there's a JSON-RPC server and it transforms whatever. So you call eth_call and it pretty much just very quickly gets directed into this function. So there's very little in between when I click the button and when this function gets triggered, which is sort of what makes this so interesting. And what does this thing do? I mean, so what are the inputs here, right? There's some context that, well, we don't really have to worry about that. But the interesting thing here is like it's the 3 arguments to Eth Call, right? And this first argument is basically just like the transaction that you want to execute. And this essentially just looks like a standard Ethereum transaction, except you don't have to provide a signature. So this is sort of like if you haven't played with Eth Call before, like at a lower level, you don't have to provide a signature. You can provide any sender address, which lets you do some interesting stuff. One thing that we do, for instance, at Optimism is we have a proxy contract, and we still want to be able to query the state of the proxy contract itself, but we want everybody else to have to go through the proxy to the implementation. So we have this modifier that's like, if the sender is the 0 address, right, 00000, then you can query the state of the contract. And on layer 1, you can't, if you can send transactions from the 0 address, you have much bigger problems than being able to sort of like query the state of the proxy contract. But it means that you can still, on the client side, you can provide whatever from address you want, and you can do interesting things like that. Then, of course, block number or hash here, right? This is just essentially you're defining the context that I want to execute my call against, right? You're saying, because at every block, the state is going to be at least slightly different, and so you want to specify, I want to execute my call against a specific block because that defines what the state is going to be when I make the call, right? Because if in one block I create a contract, if I do the call against that contract in that block, okay, it'll have code and it'll execute and I'll get the right result, maybe. And then if I do the call against the previous block, I'm going to get nothing back, right? So that's important. And then overrides here is kind of like a little known feature. I don't know if it's actually standardized, but it's definitely available in Geth. So if you make an Eth call, if you use Eth call against a Geth node, you can provide this like state override, which basically just fully you can modify the code of any account, you can modify the storage of any account, and it essentially allows you to do like cool dev tooling where you want to sort of what would happen if the code of this contract were this or this, right? Like an interesting use case for this would be if you wanted to create like mock contracts, right? If you wanted to sort of change the behavior of a contract on the fly, then when you make the call, you can provide this state override and the contract will behave in some other way. But that's sort of a Geth specific thing. Anyway, then we get into this do call thing. So this is actually the majority of the interesting part of this method here. And once you get inside here, you really get to the sort of the meat and potatoes of like what a call does, or like what a sort of like vague Ethereum transaction thing looks like. And you can see here, right? So now, first thing we're doing is we're getting the state at the block hash or the block number that we referenced. So that's what I was talking about before, right? You need some context to execute against. So you pick a block, you pull the state at that block. And then here's where the overrides come in. You can sort of modify the state arbitrarily with these overrides, but only, this doesn't actually modify the state permanently in the Geth node. It's only for the sake of this one Eth call. Usually you won't use this, but it's interesting if you want to. Then some stuff here that you don't really have to worry about. That's just sort of like cleanup once the thing is finished. And then we sort of, now we're getting very close to being into the EVM. So you can see there's very little code in between when you get in and when you actually start executing the EVM. This first thing here is, so it's interesting, this concept of a message and like the difference between a transaction and a message. In the EVM, usually you'll refer to messages where in this case, I won't actually look at what they're doing here, but the interesting thing is, here's what a message looks like, right? You're calling a contract. It's about these contract calls, right? You're calling a contract. You're calling from a specific address. There's, well, in this case, there's a nonce. There's some value that you're providing to the call, right? This is if message.value, and then then there's like data here as well, whatever. But this is slightly different from what you might imagine in a transaction, right? Like a transaction doesn't really have this from field, for example. Like if you've ever created a transaction, you have a signature that you provide along with the transaction, and then based on the signature, you recover the sender, and that becomes the from field. But that's sort of like very specific to the way that the initial Ethereum transaction format worked, where you have a specific format and you have an ECDSA signature, and that's how you get this from address. But it doesn't have to be that way, right? You can use BLS signatures, you can use whatever signature method, you can use sort of any arbitrary sort of mechanism to decide who the thing came from. So there is sort of this difference between a message and a transaction that's important to think about. But really, all we do, like in the case of Eth Call, we're kind of just transforming this transaction thing into a message just for the sake of, because it's what we have to give the EVM. But because in Eth Call, you provide a from field, this is a little different than what would happen in a real transaction, because in a real transaction, you would have to recover the signature or recover the address from the signature. Cool, next step, basically generate an EVM instance. So this is just like you create a struct, whatever. Doesn't really matter, it's not super interesting. But like this is basically the most interesting line of code in the entire thing, right? This core.apply message. And it's essentially saying we have this EVM and it's loaded with a specific state. And we are going to take this message that does something to the state, and we're going to give it to the EVM, and we're going to tell the EVM to go do a bunch of work, and this is going to mutate the state somehow. So like, again, there's very little happening between when we started the function and when we get here. Like this is when the most amount of work that we're even doing is going to happen in this function.
So Kelvin, what were all the gas manipulations at that level? So there was one with the message, right, and then there in the other gas.
Mm-hmm.
Gas manipulations there outside the EVM?
Yeah, there are some gas calculations that get done inside of here. Some of this is like EIP 1559 stuff that I haven't really looked at yet. So like an interesting thing to note about Eth Call is that there's a global gas cap, which is like this. Essentially, nodes can decide to set a gas limit that is much higher than the block gas limit for Eth Call. And essentially, it'll say, like, if you did not give a gas limit, we're going to set it to this gas cap that is not necessarily the block gas limit. It's going to be, it can be like 75 million gas, some crazy amount.
I saw earlier in the code there was also a 5-second limit, right? Or is that something else? Like there was something like 5 times time.second, like way in the top level function.
Wait, where?
Call. Yeah, 5 times time.second.
Okay. Where is that? I'm assuming, yeah, okay, so it's a timeout. Essentially, it's like if the call does not complete within 5 seconds,
Right,
then,
both a gas and a time limit.
yeah, both a gas and a time limit.
In the context of like Geth code, is a message the same thing as a call? Like is a message is represented internal calls?
I do think, I guess we'll hop into the EVM in a second here, but I believe that they use messages everywhere. I think it's the same thing as a call.
Could you step into the definition for two messaging app?
Yes, absolutely.
And then to the definition of types of message.
Yep.
Here I saw that in a future PR, this will give.
That's been there for about 2 years, so take that with a grain of salt.
It's a bit of an awkward struct because
Yeah.
things like nonce and all the gas details, except for the limit, like those are only things that are part of transactions and non-calls.
Right.
There's not really value in carrying them through.
Right. It's definitely a little weird. I'm not exactly clear why there's a nonce here. It doesn't feel like there should be. They probably, I have a feeling they use it once in the EVM or like at the beginning of this function here, apply message, and then never again, which is very awkward.
Because of like some weird contract creation nuance thing, because for regular creates the address.
Yeah, true. Because I guess it is, because I guess it is, the contract creation is based on the nonce. You could pass the nonce through, or maybe load the nonce when you want to do the contract creation. I don't know.
The way that this stuff works in Python is that you pass in the message and the transaction to the like create and the EVM functions, and you have to do that anyway because you have to have something that answers the TX origin opcode.
I see. Okay, interesting. Well, I guess we'll find out. This is also a slightly newer version of the code. Like I've been mostly working on the optimism fork, which is a little bit older. So there's some things here that are sort of tweaked since the last time I've looked at it. But yeah, I guess we'll get into the most interesting thing here, which is just apply message, right? So we're taking an EVM, and we are, and in this case, an EVM has sort of a state attached to it, and we apply a message. We basically modify the state of the EVM. I guess this is, if you're not so familiar, like this is the weird thing about the EVM is that it's kind of like a stateful thing, right? Like there's this separation between, it's not just the interpreter, it's also like you have the state attached to it, which is just, it makes it a little weird to think about. And of course, apply message does this weird annoying thing, which I don't quite understand, which is that it creates a state transition and then transitions it. So sort of like passing through to here. So yep, now we get into like the meat of how the EVM basically works, which is pretty interesting. So step one is the pre-checks, right? So this is very standard, like what you would imagine happens at the beginning of an EVM transaction, so you're checking the nonce, right? You want to make sure that the nonce that's attached to the transaction is actually the nonce that's attached to the account. You're going to buy, well, you can read it here. You're going to pay the transaction fee. Then you're going to, you have to make sure you have enough gas left. You're going to make sure that you will buy that gas. So you'll basically like pay out of your account, and then this message will get gas that can be used during the execution of the transaction, and some other stuff here. So essentially, this is just like, can I execute this message? And then once I'm finished with this step here, I'm ready to execute. I have gas available to me that I can use for the rest of the transaction. We can look at this function if people are interested, but you've got some like EIP 1559 stuff that I don't really want to look at because it's just, good God. Let's hide that. But you can see like this makes sense, right? You can, you check the nonce, then if you want to check the nonce, so you can start manipulating this and make it so you don't have to check the nonces. But if you want to check the nonce, then get the nonce, then make sure that the nonce is equal. If it's not, blah, 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 blah.
Wait, this is weird because even before London, there had to have been code that said things like the transaction has enough to pay for gas.
Yeah, absolutely.
So why is that code not in this function, but the London code is in this function?
It is in this function. Buy gas. It's very, yes. Wonderful. I don't know why it's built this way. But yeah, so buy gas. So you do the nonce checks, which makes sense. And then you buy gas. And buy gas is basically, do I have enough? I'm going to see how much gas I want, which is the gas that the user requested times the gas price. That's the amount that I need to pay. If
I guess if I was architecting this, I would have dumped all the London stuff into buy gas.
Yeah. But yeah, so there you go. So you make sure that you have enough balance to buy the gas that you want. Right. Then if you, then there's this gas pool, which is basically like, the block only has a certain amount of gas available to it. So if you requested, 10 million gas, but there's only 5 million gas left in the block, you can't do that. So that's where you would throw an error here. But if you got past this, then you're going to add the amount of gas that you requested to the amount of gas available for the state transition. And then you record the initial gas, which is basically, it's used later for refunds, I believe. And then you subtract the amount of gas that you wanted to, you subtract the ETH cost of the gas from your account. So there you go. So you're set up, you've checked your nods, you made sure that you could pay for the gas, and you're ready to go. Then there's sort of this like setup stuff, which isn't super interesting, right? You're just sort of like creating references to stuff. If you're not aware, in an Ethereum transaction, if you don't have a message target, it's considered a contract creation. So you can also this is another interesting thing, you can do contract creations inside of an ETH call if you wanted to. I don't know why you want to do that, but you could do it. You can also do interesting stuff. Mark pointed out to me the other day that you could, maybe not with a contract creation, but you can, well, I guess you could. So in a contract creation, when you run a NIT code, you can do whatever you want in the NIT code. And you can kind of use that as a way to like run arbitrary EVM code on chain. So you can, I don't know, you can just sort of like build, you can just write scripts and then run scripts as like ETH call and then force Geth nodes to do work for you, I guess. Okay, great. So we'll store, whatever, set up a bunch of stuff here. Then there's this intrinsic gas thing, which gets much more complicated after London, but you can sort of think of it like the 2100 base gas cost. Imagine it's last year and we don't have to think about London. Then it's like the 2100 base gas cost plus the data cost, right? So there's, what is it, like 16 gas per byte, depending on if there's 0 bytes or non-zero bytes. So you do all this stuff and you figure out how much gas, just like not even starting to execute the transaction, just how much gas do I need straight up to pay for that. And I pay for it here, great, right? And then there's this, more stuff. If I added a value, then I'm going to try to transfer the value. If I can't transfer the value, then I have insufficient funds, and I'm going to return an insufficient funds error. Then there's this access list stuff that I don't want to think about because it gets too confusing. But if you're interested, this is more London stuff. Or no, this is, when was access list added? Berlin? Berlin. And then we get finally to like the actual, now we're ready to do the sort of call, right? And you just have this if statement. If it's a contract creation, I'm going to do this EVM.create function. If it's not a contract creation, then it's a contract call. And I'm going to do EVM.call. And EVM.call has this interesting behavior that for contract creations, you do not increment the nonce here. But for, well, you do increment the nonce inside of create. This is where it gets confusing. So create itself will increment the nonce. But call does not increment nonces. But because you need to increment the nonce, because it's a transaction, you increment the nonce here. And this adds a lot of annoying complexity if you want to do smart contract or like contract wallets. You know, like we had this problem with Optimism where we were like, well, it's a contract wallet, but it's meant to be like a user. So we want to like increment the nonce, but create also increments the nonce. So at one point we had a bug where it would increment the nonce twice, and it just created a lot of headaches. So, I mean, it kind of makes sense, right? I mean, create itself increments the nonce, call it doesn't, but you need to bump the nonce no matter what, but you don't want to do it twice, so it kind of makes sense. Anyway, this is where we're very close to actually executing bytecode, which is exciting. I'm going to go into call because I think create is fine, but I guess both are interesting, but call is more interesting in my opinion. So here we are. Now we're very, very close to actually executing EVM bytecode. Okay, yeah. So this is an interesting thing that's been here forever, which is this no recursion config. Do you know why this exists? Apparently, there's a configuration that allows you to not ever go beyond depth, the top level call. Why you would do that, I don't know. But let's ignore it. So this is also interesting. There is a maximum call depth limit, which is what, like 1024. So there's a maximum call depth limit, so you can't just keep making calls down. And, but I believe that it's no longer possible to actually hit this call depth limit with the current gas limit because there's another, I think EIP 159 or something, introduced another behavior, which is that I'll show you down. Actually, it's hidden very deep in here, so I won't show it. But calls can only pass 63/64 of the available gas to the child call. So if I'm in a sort of call frame and I make another call frame, I can only pass 63/64. So there's like a limit to how far down I can go before I just don't have enough gas left to even make another call, and it's much less than 1024. So this check still exists, but I don't think it's possible to hit it unless you have an extremely high gas limit. Even then, do you know what the gas limit would have to be?
I mean,
we can calculate it.
Start with 21,000 and then 64 over 63 to the power of 1024, which is going to be about e to the power of 16 or 10 to the power of around 6.5. So somewhere in the million. It'll be somewhere around 100 million would be my guess, but let's see. You need double, yeah. Times.
Oh, sorry, this is the wrong one.
1,000 times that to the
1024.
Yeah. So it should be in
Jesus.
How many digits does that have?
How many digits is that?
713, 73, 200. Okay, I said 100 bill.
So 200, is that 200 billion?
Yeah.
200 billion. So if you have a gas limit of 200 billion, then you can hit the call depth limit.
It's a bit higher because we didn't take into account like internal calls, but yeah.
Yeah, okay, true. There's also more, there's more cost than just the 21,000.
Where does that formula pop from? The 63/64?
So the 63/64 is hidden in here, but there's a, I mean, I'm sure I can find it somewhere.
Down to where the call opcode is processed, you'll probably find it there.
Yeah, gas call.
The original reason behind this was basically because it was back in the early days, there was a security attack against a lot of contracts where an attacker would self-call themselves like 1022 or 1023 times, and then he would call a contract, and that execution would fail when the contract was not expecting it to fail. And with the 63/64 rule, like basically the only constraint on execution is gas, and so contracts don't have to worry about that.
Right, because if you get right to the limit, you make a call to the target contract tries to make a call out. Let's say it makes a call to a trusted contract. It assumes the contract will succeed because it has enough gas to do so, but it's out of its depth and it fails. But yeah, so here's where it is, EIP 150. So you basically, you take the available gas, you subtract sort of the cost of doing the call, and then the actual gas that you're allowed to use is the available gas minus the available gas divided by 64. And then there's an interesting thing here. You can actually, like, if you design this carefully, you can force this to underflow, and you end up getting this like huge gas value here. And then Geth like implicitly checks this somewhere else, so you can't exploit it. But it is funny that you can force this to sort of produce a ridiculously high amount of gas. But there you go. So where are we? So here we are. We check the call depth limit. Again, we try to transfer value because you can attach value to any call in the EVM. And yeah, and then, well, what is this? So, okay, here's debug tracing. Who cares about that? Oh, here, well. Oh, okay, that's interesting. I mean, so there's some like interesting, like, this is the weird thing, right? There's like very, very specific EVM behavior that you have to implement, and like one very specific EVM behavior is if the account does not exist in the state and it's not a precompile, and so you're sending a transaction to it with no value at all, then you're just going to return, right? Because if it doesn't exist, then it doesn't have any code in it. And if you're not sending any value, then you don't have to add an entry into the state trie, so why bother? And you just return sort of like without any data. You just say, oh, there's nothing happened. But of course, if you give a value, right? So if you don't hit this if statement, then you're going to create an account in the trie because you are going to attempt to transfer value to that account. And you've already checked that you can transfer, so you know that the transfer is going to succeed. So you're going to create an account in the trie, and then you're going to sort of modify the balance field of it. So it's not going to be, it's no longer going to be the an empty account with the empty account code hash and whatever. More debug stuff, kind of an interesting. Precompiles are cool. You know, you can actually, like, this is a great thing to just read in, I think it's contracts. And you can just see like how the precompiles work. You can, so each, I guess the way that they do this is that for every, you have these structs, and each one of them has a required gas function and a run function. And you can just see, like, you know, what happens when you do EC recover, and you know, this is EC recover under the hood. This is where that interesting little Infura snafu. Well, where was it in identity? Data copy. They call it data copy. This is where this interesting the Infura snafu was from a few months ago, where data copy, all it does is it returns the input. It doesn't actually copy, like it doesn't create a copy of the input, it just returns the input. And in this case, the input happened to, I can show you later, but it happened to be a reference to a to memory. So you could, like, essentially by manipulating memory, you could manipulate, or sorry, but by manipulating memory, you could manipulate like the return data, and you can do this weird thing. That was a Geth bug. But so for the most part, people don't really call precompiles except for maybe like EC recover. If you're interested, just go read them because they're cool. It's probably where I would assume if there are any real remaining bugs in Geth, that they probably live somewhere in this. So if you, not if you want to exploit Geth, but if you want to maybe find something interesting and report it to people, I'm guessing that it's probably somewhere in here. Just because people don't use the precompiles, and so people don't give weird inputs to the precompiles, and so people don't find issues with them. Oh, really? Yeah. I guess, oh yeah. Oh, nice. Okay, so some of them, I'd still recommend people take a look at this and kind of get an idea how they work. Where are we? Okay, so if we're not running a precompile, we're going to actually run some EVM bytecode, and we need to load the code first. So we pull the code from the state. If there's no code, then we don't do anything because there's no code. So that's pretty straightforward. If there is code, we essentially, the way that Geth does this is a little weird. I wouldn't do it this way, but they create this like contract object that they execute, which is a little, whatever. I would do it with a function, but c'est la vie. And here's where you run the interpreter. So you essentially load the sort of the context, and you give it a bunch of code, and now you run the interpreter. And running the interpreter is pretty cool. It's kind of what you would imagine, right? There's well, setup. There's no, we wouldn't hit this in that case because we already did this check, but if there's no code, we don't run it. And then here you set up like the memory, and you set up the stack, and you set up the context, which is the memory, the stack, and the code that you're running, and the address, and blah, blah, blah. And then you get down to here where you essentially, you have a program counter, and you get the opcode at the position, and you figure out, you look up what that opcode is supposed to do, and you run the opcode. And this opcode might manipulate state, or it might manipulate the memory, or it might, depending on what the opcode does. There's some interesting validity check about like if there's there's only a limit to how many stack elements you can have and whatever, but really you're just sort of like going opcode by opcode, and then maybe if you have a jump, you can jump to a jump dest. And then there's currently rules about, you have to jump to a reachable jump dest. It can't be a jump dest that sits behind a push opcode, because then it's not a real jump dest, it's actually a push, and there's all these interesting things. But oh, my phone is, yeah, it's very, if you're interested, at this point you have, it's less stateful for the most part, because you can kind of think of this as a function on, well, you can think of this as a function on the state plus, you start out with, no memory and no stack, and then you just sort of execute a very clean, pure function from there. And then here's where that Geth bug was, where before it looked like this. And instead of that, and it turns out if you do that this ended up pointing to memory, so the return data was a pointer to the memory, and you could manipulate the memory, and that would manipulate the return data, which is not the return data is supposed to be a separate thing. So there you go. Interpreter is pretty straightforward. But eventually, you're going to run these opcodes, and you're going to hit either a revert or a return, and depending on what you hit, you're going to get some sort of return value and potentially an error. And the error can be an execution reverted. That's considered an error in this case. And if there is an error, then we're going to revert back to the state before we did the transaction, because that call should not, or before we did the call, because that call should not have an impact on the state if it reverts. And then we return. It's very, at that point, we ran the code, and it's gonna give us something back, and it's either gonna be a return or a revert. And there you go. And so this return value is going to be just bytes, and this error will tell us whether it reverted or returned. And that's also what will you can look inside of instructions.go and look for opcall, and it'll give you a little more context of like, oh look, we're gonna pop all this stuff off of the stack, and we're going to figure out what the target address is, and we're going to do this. We're going to do the call. So this is that function again that we were calling. So this is if you were doing it if you used the call opcode inside of a contract, for instance, then you'd get return the return value, the amount of gas that you've left, and whether it's an error or not, and then. This is where that Boolean of the success status of the call that you made, if there's an error, then the Boolean is going to be set to 0, and otherwise it's going to be set to 1. And then this is if, oh, that's interesting. Okay, yeah, oh, right. You can provide that parameter to call, which is essentially here's where the output is going to live, and it's going to copy the return data into that memory location that you requested, and then it's going to add back as much gas as you did not use. Cool, and there you go, right? So it does a call. It can modify state, right? You can have instructions like store, and this is going to pop stuff off of the stack, and then it's going to literally just go and set state. Boom, easy, right? This is going to manipulate the state try, and that's like how store works, right? Load is very similar. You're going to pick a location, and then you're going to load the value at that location in the storage slot at that location. This is a very interesting file to just sort of read through and get an idea of like literally what every opcode that is actually doing under the hood. There you go. So we return, and now we're back at the top level. Create is its own beast that we don't really have to look at very much, but you figure out the address, and it's very similar where you run the init code, and just like you would run the contract code when you call it, you run the init code, and the code that gets stored in a create is just whatever the init code returns. So here we are, we're back, we're done, right? We did our execution, and maybe in the execution we keep making calls down, and it sort of does this in a recursive manner. And then at the end of it, we get one final result, which is this is bytes, and this is the amount of gas that's left, and that's whether there was an error or not at the top. In this case, at the top level. Then you do gas refunds at the very end, right? So there's all these rules about if you overwrite an store, if you overwrite a non-zero storage slot with zeros, you get a gas refund, blah blah blah. And I'm going to ignore this because I have no clue what this is doing. And then you pay the Coinbase.
It's just calculating what the premium fee is for any account by 5.9. And I guess it's just adding that to the miner.
Okay, yeah, effective tip. I see. I see. Yeah, okay. But there you go. So at the very end, you pay the miner, right? So you did your execution, and then now at the very end, depending on how much gas you use, you're going to pay the miner, and then you return it, right? So you return the execution result. So you did all this work, and now you returned some data, and maybe it had an error, and there's some amount of gas that you used. And gas used is where we use that initial gas, right? We recorded the initial gas all the way at the beginning, and now we use some amount of gas during the execution, take the difference of that, and then boom, that's the gas used. So where are we? We're almost done here. All the way back to API.go. We did all that work, apply message, right? Now we get a result and we get an error. So if it's a VM error, we're going to return it. You'll see how that gets handled. It's interesting. But this is a new feature. Don't really worry about this. This is if there's a timeout, if it takes too long, just for the sake of making sure that the Geth node doesn't get overwhelmed with ridiculously complicated calls. And cool. Otherwise, if there's some non-VM error, then we'll throw it. Otherwise, we'll just return the result. So now we're all the way done with do call, and now we just go back to call. The very last thing is this interesting thing, and this is sort of new with Geth, which is just they nicely parse errors in the sense that there's a 4-byte prefix that I guess is standardized now, which is like the hash of, it's like error string, and you take the first 4 bytes of that. And so this thing, essentially it says, like, if it starts with this thing, I'm going to treat it like a string error. I'm going to parse it, and I'm going to return it in a nice way so that if I make a call and it, and Solidity reverts, then I'll see why it reverted. Whatever. That's all this is doing. Just parses the return data. And then at the very end, it just returns the result, right? It just returns whatever return data that came out of the contract, and potentially this. And another error. I don't know where this other error comes from, but I don't feel like looking at it. But that's the high level. This is, it's like how the EVM works, right? You just go in and you set up a bunch of stuff, and then you go into you do a bunch of pre-checks, and this is sort of like the, what you think, how you think a transaction works, right? You check the nonce and whatever, and then go and execute EVM bytecode, and that's going to return some bytes, and then you're going to return that out. Very sort of, there you go. That's like the EVM in a nutshell, right? In call. And then as bonus points, gas estimation is pretty much just a binary search on of like repeatedly executing. Where is it? Where is it? Where'd it go? This looks very, wait. Okay, here we go. Essentially, you just check, can I execute the transaction? You do the call, and if it doesn't revert, then great, and that's how much gas you need. And if it does revert, then add more gas until you find a certain amount of gas that where it does not revert. And if you can't find that amount of gas, then throw. Or just say, like, I can't find that amount of gas.
So pre-call with extra gas. It's like a pre-call with extra gas.
Yeah. I mean, you basically just want to find the lowest amount of gas that you can provide that will still result in not a revert. But, of course, that will fail. If you have a contract that always reverts, then there's no amount of gas you can use that will succeed. Or if you wrote a contract that changed its behavior depending on like if the gas left was even or odd. You know, gas estimation could fail, but that's such an edge case that, and like if you do that, you should know that you're going to have problems with gas estimation anyway. So.
What's the tolerance for the binary search set?
Sorry, what was that?
The tolerance for the binary search, how far you go there, where is it set?
So I believe that. Wait a minute. Yeah. Okay. So I guess it will try to find literally the exact amount of gas down to a one gas difference of succeed and not succeed.
Only if that's the smartest choice.
It's very computationally expensive for the node.
Yeah, very suboptimal. Because like
Mhm.
most transactions, you should be able to use the remaining gas after the high as I can for how far below the high you can go.
Yeah.
And how about situations where the estimate gas changes depending on the state? Like if you
Mhm.
move the two blocks, and the same call has a different estimate gas.
Right. Like it could be more expensive 2 blocks later, which that's valid. I mean that, you know, maybe this tolerance should be do this and then add, you know, X amount of gas on top of that. That's very valid. Somebody should complain. And there you go. We found one thing in Geth to complain about.
I thought that was a feature.
Yeah, I mean, I think probably for 90-something% of cases, this is completely fine. And if anything, the gas usage will decrease. Well, I don't know. I could see. It does seem kind of sus that if the gas usage increases by like 1 gas, that all of a sudden it fails.
We've had failed calls just based on estimate gas. We made an estimate, and
Mhm.
we put that estimate in,
Mm-hmm.
and then we repeatedly try to call it. At some point it fails because that same estimate is not valid anymore.
Wow, interesting. Okay, they should, yeah, then they should definitely, it seems like you want a buffer there of like at least, you know, 20,000 gas or something. I don't know, fine. Yeah. Cool. I mean, that was kind of long, but does anybody have questions about how this works? You know, it's pretty, in a lot of ways, it's very straightforward, even though there's a lot to it, but there you go. Thank you. Please clap.
The part about VM error,
Mm-hmm.
you were going to mention that's like a special case in which you have a result and check if it's a VM error versus that kind of feature. What's happening there?
Where are we?
You have 2 errors there.
Yeah. So I believe that the VM error is like, where are we? Come on. Yeah.
Can you go with
I don't know. I mean, there's like a difference if you look, for instance, like error insufficient balance. Like there's certain errors that are, I essentially are errors, like a revert is fundamentally different from like one of these errors. So I think I'm pretty sure it's just checking the difference between like, oh, it was just a revert. It's not, and like it's still, you can see it still gets returned as an error either way. I believe it used to be returned separately. So that I think there was like a separate VM error and then error, and now it's just one thing. But like this sort of error that's like, oh, there's an error execution reverted, is very different from error insufficient balance. Because this thing, like, oh, the thing completed successfully, but the subcall reverted. This is, we didn't even do the call because you didn't have enough balance to do the thing. So it's just sort of differentiating between those two, which I think is sort of a weird API design, to be honest. I think it makes more sense to have the separate VM error that they used to have.
Why is it setting gas 0
If the, well, yeah, so I guess there's cases in which you can have an error, but it's not a VM error. So what? I wonder where that happens. Error invalid opcode. Yeah, okay, there's an example, right? So you have, if you use an invalid opcode, then you burn all gas immediately. And I guess apparently any of these errors will force you to burn all gas immediately, which is interesting. Cool. All right. That's all I got unless people have more questions. The magic of Geth.
This might sound like a noob question, but when you make changes to Geth,
Mm-hmm.
and you commit that code, and then you try to, I don't know, sync with other Geth nodes, do they know that you're on a different commit? And do they know if that commit is valid or like accepted across other nodes or not? Or can you do that?
No, you can modify this as much as you want. And I mean, I guess maybe if you somehow change the behavior of Geth in a way that would, I don't know, it would have to be noticeable to other nodes. Like if I just put if I put a debug log in here, none of the other nodes are going to notice that. It would have to be some noticeable change in like how my Geth node interacts with other Geth nodes, which seems.
Are there protected parts that you make change to this, then it's like the other nodes just reject seeing messages? Should you build something on that if it's not already there? Just out of curiosity.
I mean, I think you like just go for it for the most part. I don't think nodes really won't like blacklist you. Plus, if they're going to do anything, they're not going to blacklist like your code. They're going to blacklist your IP address or something because you're spamming transactions or something, or you're not, you're being a bad peer or something. But no, I mean you can pretty much manipulate whatever you want inside of Geth, which is the magic of it. And you can I don't know, add a bunch of log statements and sort of like add a bunch of extra analytics, and this is what all the big node or Etherscan is going to have like a custom version of Geth where they log way more about what's going on during the transaction.
Yeah, like middleware.
Yeah, I mean that's what all these people have to do, and it's fine. You can't tell the difference, so. And people don't care. All right, we can do more questions later, but that's the TLDR. Eth Call. I wouldn't call it a TLDR, but it's very TL. Take this with me.